Okay, welcome to this video. In this video, we will talk about non-deterministic finite automata. Yeah, non-deterministic. What is non-determinism? That's the first question. Non-determinism, that's a very important concept in theoretical computer science. And to understand what non-determinism is, let's recall, why did we call the DFAs deterministic? Yeah, let's go back a little. Yeah, for example, here we had a DFA. We call it deterministic because in every state and for every symbol that we read, there's precisely one following state. So for example, if we are in this state and we read an A, we have to go to here again. Yeah, and if we are in this state and we read an A, we have to go to here. There's only one option, what's the next state. And this is deterministic behavior. Now in non-deterministic machines, this restriction is removed, yeah? So everything else stays the same, yeah? Here's a non-deterministic finite automaton. Everything else stays the same. We have states, we have a starting state, we have a set of accepting states, but the restriction is removed that there must be precisely one following state for a symbol, yeah? For example, let's look at this state here. We have two outgoing A arrows. Yeah, so if we are here in this state and we read an A, there are two possible ways to go. Okay, now you should be really confused. You should be asking yourself, then how do we know whether we accept a given string or not? Yeah, then what does the automaton do if it is in this state and reads an A? Okay, you can think of it in the following way. Okay, so we will read the input string, as always, symbol by symbol. But whenever we're in a state, and for example, if we are here and we read an A, then the universe will split into two parallel universes, yeah? In one universe, we are here, and in a parallel, like in another universe, we are in this state now, after reading the second A. Like if you read AA, then you are either here or here, yeah? There are two possibilities. And a word gets accepted if there is at least one of those parallel universes where the word gets accepted, yeah? So even if there are 1,000 universes where the word gets rejected and only one word gets accepted, then in the end, the NFA accepts this word, yeah? So let's make it an example. Let's look at the word AABA. We want to know if this non-deterministic finite automaton accepts the word AABA, yeah? So when we start, we'll read the first A, we have no choice, we have to go to here, yeah? But now we read the second A, we already have a choice, yeah? So for example, let's go to here now. And then we read a B, so we could go to here. And then we read another A, and then we go to here. So in this parallel universe that we are just in, we ended up here and we rejected the word, yeah? But there could have been other ways to read this word, yeah? So we don't stop now, yeah? Let's try another way. For example, A, B, A. Okay, we rejected again, but let's keep trying. A, B, A. And see, in this universe, we accepted, yeah? So there was a path, A, B, A, to read the word and end up in an accepting state. So this means the word AABA gets accepted. Yeah, that's because there was at least one way to read the word AABA and end up in an accepting state. Yeah, this way, AABA. And if we have found one such way, then we don't care anymore. The word gets accepted, yeah? Okay, let's look at another example. The word BBA, for example, yeah? So we start, we read a B. We have no choice, we have to go to here. The second B, we have different options, yeah? So let's go to here maybe first. And then we read another A. Okay, we could end up here, or we could end up here, or we could end up here. But these are all rejecting, yeah? So let's see, was there another way? Yeah, we could go B, A. But this is also rejecting, yeah? And these are actually all the possibilities, yeah? We have here two choices. So after the second B, we are here or here. And after reading the A, we are here or here or here. And all these states are rejecting. So there is no way to read the word BBA and end up in an accepting state. And only if there is no such way to read the word and end up in an accepting state, then we reject. So the word BBA is not contained in the language recognized by A. Okay, let's look at one more example. The word ABA. Yeah, the first letter is an A, so we go to here. The second letter is a B, but from this state there's no outgoing B arrow. Yeah, so we already see there is no way to read the word ABA and end up in an accepting state. Yeah, because, well, we cannot even read the second B. Yeah, after this state we are stuck. And if we are stuck, you can imagine that this parallel universe just disappears or something. Yeah. So after here there are no universes left. And so there is also no universe where we can reach an accepting state with the word ABA. So that's why ABA gets rejected as well. Yeah, now you might wonder, why do we consider such weird automata? I mean, non-deterministic machines do not exist in reality. Yeah, they are a theoretical construct, but they are extremely helpful for theoretical purposes. Because for many problems, there exist very natural, very easy algorithms that are non-deterministic. And if you have this theory of non-deterministic machines, then it's much easier to examine those kinds of problems, yeah, and to research about those problems. And also the very famous P versus NP problem, one of the most famous unsolved problems in modern mathematics, that's about non-determinism. Yeah, the N here stands for non-deterministic. But I won't go into detail here now, this is a little more advanced. Yeah, so let's stay with the NFAs for now and let's look at another example, why the NFAs can be helpful. So here we have an NFA with 4 states, and it is really non-deterministic because see here in this state we have 2 outgoing B arrows, yeah? So if we are in this state and we read a B, we have the choice, like do we go to here, like do we loop around, or do we go to the next state? And I would recommend you to pause the video now and think for a moment, what language does this NFA recognize? Like what is the set of strings that gets accepted by this NFA? Okay, so I hope you thought about this and I hope you came up with the right answer. Okay, let's think. To reach this state, well, we have to reach this state if we want to accept a word, yeah? And to reach this state, the last symbol must be an A or a B, so basically it doesn't matter which symbol because our alphabet consists just of A and B, yeah? And before that symbol also doesn't matter, yeah? So we read 2 symbols, the last 2 symbols totally don't matter, but the third last symbol must be a B to ever reach the state, yeah? So if we accept a word, then the third last symbol must be a B, and then there are 2 more symbols, A or B. And in fact, every such word where the third last symbol is a B gets accepted, yeah, because you can just read all but the last 3 symbols in this state, yeah, you can loop around here until there are only 3 symbols left, and when it's a B, then you go to here, and then 2 more symbols, yeah. So actually, this automaton accepts precisely the words whose third last symbol is a B. Yeah, so strings with at least length 3. Yeah, of course, to reach the state we have to have at least length 3 because we read 3 symbols on the way at least. And the third last symbol of W is a B. Well, I hope this sounds familiar to you. Let's take a look to the last slide here. The words length at least 3 and the third last symbol of W is a B. We constructed a DFA for this language last time. And actually this DFA was quite complicated, yeah? It had 8 states, 4 of them are accepting, and if there wouldn't be those names in the state, it would be quite complicated to realize what is the idea behind this machine, yeah? And now let's look at the NFA. It looks so simple and it recognizes the same language. And I just want to mention another metaphor, like how you can think about non-determinism. Non-determinism is often expressed with a phrase like guessing. The automaton is guessing which way to go, and if there is a way for him to guess correctly, he will do so, yeah? Yeah, so imagine this automaton reads this word, yeah? So at first we read an A, okay, we have no choice, we loop around here, yeah? And then there's a B, so we could go to here, or we could go to here, yeah? But to accept the word, we know this is the third last symbol and not this one, yeah? So the automaton guesses now to loop around here and not go to here, yeah? and then we read another A, and now we read another B, yeah, this B here. So now we guess to go to here, we guess that this B is the third last symbol, and then we just verify it, yeah, there are just 2 more symbols to read. We verify this by going to here and actually ending up in the accepting state at the same time when we're finishing the word. Yeah, so this way gets accepted because there is a way for the automaton to guess correctly. Yeah, like the first guess, the first time we read a B, the guess should be take the loop. The second time we read the B, the guess should be go to the next state. And if we would have guessed wrongly in the first place, yeah, so if we'd start reading the A and then go to B directly with the second symbol, well, then there's another A, okay, go to here, and there's another B, okay, we go to here, but now we want to read another A, but here's no outgoing A arrow, yeah, so this parallel universe just stops to exist at that point, and there was not a successful run for this word, but because there is another successful run, this word gets accepted. And as another small exercise, I recommend you to think about why this word doesn't get accepted, yeah? So think about why there is no way to read this word and guess correctly, yeah, whenever we read a B, guess correctly to end up in this state when we finish the word. Yeah, why is that not possible? So that this word gets rejected. Okay, and I guess that's it for this video. So thank you for watching.